Hello, Mr. Waters, and good morning and happy almost Easter. I hope everyone's looking forward to their Easter break. Okay, so first off, I want to tell you that I have your tests in hand and I'm in the process of grading them. We'll get those back. You'll be able to see your grades on Canvas at some point during spring break. And then we'll get them back. We'll think about, if you're interested, we'll think about test rewrites when we come back from spring break, okay? So here I'm going to give you a lesson here, a quick introductory lesson to our next unit, which is about sequences and series. Now there's going to be some homework here, but it's not going to be due until the Tuesday after we come back, which will be the next blue day after this one. So let's be clear, the Tuesday after we come back. Okay? All right. So a sequence and its combined concept called a series are a very important concept in math, and they're used in a lot of different fields and for a lot of different purposes. And so today and our next unit that we're going to work on here is about what they are and how they work. Okay? Now, first off, a sequence, what a sequence is a very simple concept. A sequence is an ordered list of numbers. So for example, 1, 2, 3, 4, 5 is a sequence. Okay? Or -3, -6, -9, -12, -15. That's a sequence, because you can see that's not just a random list of numbers. It's a list of numbers that has a pattern to it. So those are both examples of sequences. Okay? Now, specifically, these we would call them finite sequences because they have a certain discrete number of terms. Right, this one's got 5 terms. This one's also got 1, 2, 3, 4, 5 terms. Right. Generally speaking, when we generate a sequence and when we talk about sequences, we will be working with what are called infinite sequences, meaning that instead of just stopping here, the pattern would just keep going for as long as we want, forever potentially. So that would be written like this: 1, 2, 3, 4, 5, dot, dot, dot. Okay? Or this one here, -3, -6, -9, -12, -15, comma, dot, dot, dot. That dot, dot, dot there has a very specific meaning in terms of sequences, and that is that the numbers just keep going for as long as we want, following the pattern established by the numbers that we've already written down. Okay, so these are both called infinite sequences, and generally speaking, when we work with sequences, those are the ones we're going to be interested in. Okay, now some vocabulary. Okay, so each term in the sequence, or each member of the sequence, is called a term. Each member of the sequence is called a term. And you can think of these numbers as like standing in a line. That's the first term of the sequence, that's the second term of the sequence, that's the third term, that's the fourth term, that's the fifth term, right? So in this one, -3 is the first term, -6 is the second term, -9 is the third term, -12 is the fourth term, -15 is the sixth term. So not only is there a pattern, but each member of the sequence comes in a very specific place. So -15 is the fifth term of this sequence, right? Okay, and 3 is the third term of that sequence. And so each term is given an n number, an n value that describes its position. in the sequence. Okay? So for instance, so we could say in this sequence, we don't know what it is, but this sequence would have a 100th term in it. So if I counted out 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10, 11, 12, all the way out and follow the same pattern out to the 100th number in line, we would say that that is the 100th sequence. Okay, does that make sense? Now, there are no negative numbers. It's just like the sequence, or I'm sorry, I didn't mean that there's no negative numbers in a sequence, but I meant there's no negative term numbers. We always start with the first one, go with the second one, go with the third number, describe the fourth number, and so we think of the numbers as like the values of a sequence as people like standing in a line. Okay? All right, so the sequences of interest to us are not just randomly generated number, they follow a pattern. Okay, so sequences follow a pattern. Right? Sequences follow a pattern. Right? Usually, the pattern is described by a formula. Is described by a formula. Right? So in this sequence here, we would see that we're adding 1. In order to get each successive term, we add 1 to the previous term. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5, 5 plus 1 is 6, 6 plus 1 is 7. So the formula for 1, 2, 3, 4, 5, ... we would say S of n, that represents that little S sub n there with a subscript n, represents the entire sequence, and we would call that n plus 1, right? That says that we start with 1, and in a formula, we start with the term of the sequence, say the fifth term, and we put that into the formula, right? So if we want, and so on, okay? That's actually, sorry, it's not the correct formula. It's actually just n, okay? S of n is equal to n, because in this very simple sequence here, the term number is also the number of the sequence. For this one, if we wanted here 2, 3, 4, 5, 6, 7, ... S of n, with that one would be equal to n plus 1, because we start with the first term, which is, I'm going to use red here. This is 1, and to generate that term, we add 1 to it. So 1 plus 1 is 2. To get the second term in the sequence, we put term number 2, which is n. 2 plus 1 is 3. To get the third term in the sequence, we put 3 in. 3 plus 1 is 4, and so on. So this is the n number, and this is the sequence number right there. Now, generally speaking, we don't bother to write out n is 1, n is 2, n is 3, n is 4. Those are just assumed within the pattern of the sequence. That's the first term, that's the second term, that's the third term, that's the fourth term. Okay, does that make sense? There's lots of, okay, this sequence here, for instance, -3, -6, -9, that would have a formula as well. Okay? All right, so here's another, and there's lots of different kinds of sequences. Here's one, 1, 4, 9, 16, 25. Okay, here you might notice that those are square numbers right there, right? So it turns out that so the next one would be 36. So the first term is 1, the second term is 4, the third term is 9, the fourth term is 16, the fifth term is 25, and so on, right? So for that one would have a formula that looks like this. S of n is equal to n squared, right? Where we would go, okay, well, all right, The first term is 1 squared, the second term is 2 squared, the third term is 3 squared, the fourth term is 4 squared, the fifth term is 5 squared. And the nice thing about writing the definitions or defining each sequence with a formula like this is that we can actually just say, well, what's the 100th term? Okay? Okay, so what is the 100th term in the sequence? Well, to figure that out, we would just put 100 where the n is. So S sub 100, that refers to the 100th term in the sequence. That's equal to 100 squared, which is, as it happens, 10,000. Okay? All right, very good. So there's that. So that's the idea of a sequence. It's a list of numbers with a formula that generates the numbers in the sequence according to what position the term is in the sequence. Okay? So if I give you a formula for a sequence, S sub n, say, is equal to n minus 4, we can generate terms of that sequence. So let's say we're going to generate, we want to know what are the first 4 terms of the sequence that has that rule, and what's the 10th term, and what's the 20th term, say. That is, if we were to write out, starting with the first one, put these guys in a list, the first term, the second term, the third term, and so on, what would be the first 4 terms, and what would be the 10th one, and what would be the 20th one. Well, in order to generate that, we can make a little table, and we'll do that first. Okay? Here's n, and here's n minus 4. Now, by the way, if this looks like, a formula for a function or something, then you're right. More about that later. So here's the first term, the second term, the third term, the fourth term. We merely put n is 1, n is 2, n is 3, n is 4 in for n to generate the corresponding terms. So n minus 1, so 1 minus 4 is negative 3. N minus 2, okay, if we put 1 in for n, 1 minus 4 is negative 3. So the first term in the sequence would be negative 3. We put 2 in. 2 minus 4 is negative 2. Okay? 3 minus 4, negative 1. 4 minus 4, 0. So these are, as you can see here, the first 4 terms in the sequence. The first term, the second term, the third term, the fourth term. And I'll write it out like that. S sub n. Now, if we want to know the 10th term, we don't have to keep, and you could see the pattern is we're counting up by 1. We're adding, one way of thinking of the sequence is we're adding 1 to each term, starting with the first term of negative 3. But typically, we're going to use this kind of rule here, because this, we can generate any term in a sequence that we want. So if we want to know the 10th term, we put 10 in for n. I'll put it over here to kind of continue. Here's n minus 4. So this would be 10 minus 4, right? Which is, of course, 6. And so we would say n, or s sub 10, is equal to 6. That says the 10th term of this sequence is equal to 6. Why? Because 6 minus 4 is, 10 minus 4 is equal to 6. What's the 20th term? S sub 20. We put 20 in for n. This is 20 minus 4. That is 16. So S sub 20 is equal to 16. Okay, does that make sense? Okay, so that's the idea. Now we can, let's say we've got another formula here. Let's say S of n is equal to 3n plus 1. Well, that says that we can generate, again, the first 4 terms in the sequence, right? And we can generate the 20th term and the 10th term by substituting the desired values for n, the position term, the position value of that term into the formula, and it'll generate the number that goes with that. Okay, so I'll write a little table here. So this will be 1, 2, 3, 4, and then 10, and then 20. And if this looks like making a t-table, then you're right. It is, just like generating a t-table. Okay, plus 1. Okay, so this is 3 times 1, so we put 1 where the n is. 3 times 1 is 3, plus 1 is 4. 3 times 2 is 6, plus 1 is 7. 3 times 3 is 9, plus 1 is 10. 3 times 4 is 12, plus 1 is 13. Okay, now the 10th term, 3 times 10 is 30, plus 1 is 31. 3 times this 20th term, 3 times 20 is 60, plus 1 is 61. So when we write it out, now you're going, oh, that's just a t-table, Mr. Waters, but when we write out the answer, the way we write out the answer for a sequence, for the first 4 terms, we will write S of n is equal to 4, 7, 10, 13, and then I'm going to put dot, dot, dot to show that that sequence keeps going, doesn't stop. And I should have done that up here, by the way, dot, dot, dot there as well. We could say S sub 10, the 10th term in the sequence is 31, and S sub 20, the 20th term in the sequence is 61. So it's just like a function, right? But we write out the values of the function in different ways, sequence-wise. Okay? All right, now I want you to go ahead and try this. Okay, so try this on your own. Okay, so you're going to put the video on pause. Okay? And then you're going to go ahead and you are going to write out right here what are the first 4 terms of this sequence, and then what are the 10th term and what are the 20th term. So what if S sub n is equal to negative 2n? And what if S sub n is equal to 4 plus n, let's say. So generate the first 4 terms and then the 10th and the 20th term, put the video on pause, then come back and see if our answers are the same. Okay, I'm back. So here, like this, the first 4 terms, 1, 2, 3, 4, and then this is going to be S of n equals to negative 2n. So negative 2 times 1, that's negative 2. Negative 2 times 2, that's negative 4. Negative 3 times 2 is negative 6. Negative 2 times 4 is negative 8. So the first 4 terms, S of n, that's negative 2, negative 4, negative 6, negative 8, and then dot, dot, dot to show that it would keep going, because really n doesn't stop for these infinite sequences. The 10th term would be negative 2 times 10, so that's a negative 20, and the 20th term would be negative 2 times 20, which is negative 40. Okay, now for this one here, okay, and 1, 2, 3, 4. So, by the way, you might be asking, do we always start with n equal 1? And the answer is yes, we do, right? Because these are intended to be discrete terms in a sequence, like numbers standing in a line. The first number, the second number, the third number, the fourth number, and so on. So this is 4 plus n, and this rule just says, well, which numbers are in that line, okay? So 4 plus 1, I'll use a different color here. 4 plus 1, that's 5, so the first term would be 5. 4 plus 2 is 6. 4 plus 3 is 7. 4 plus 4 is 8, right? So this would be S sub n is going to be equal to 5, 6, 7, 8, dot, 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 dot. S sub 10 would be 4 plus 10, which is 14. And then S sub 20 would be 4 plus 20, which is 24. So that's how that works, assuming I've done my arithmetic correctly and working out these numbers. So that's the idea of a sequence, right? And there's all different kinds of sequences, okay? Now, one thing that you can do here is that you can, if I give you a sequence, you can try to figure out what the formula is, all right? So, for instance, if I give you the sequence, so guess the formula. So I'm giving you this sequence here, 2, 4, 6, 8, 10. And then so use a little bit of deduction to try to figure out what the formula would be. So you can see that this one is just sort of, this one is 2 times 1. And we can see that, oh, 4 is 2 times 2. 6 is 2 times 3. 2 times 4, 2 times 5. So you can see we're starting with n equals 1. And then to generate each term in a sequence, we're multiplying that position term by 2. So we would say for this formula, the sequence formula is 2n. Okay? Or how about this one here? This turns out it's a very important sequence in the scheme of math. But you can see here, if we're starting with, if this is the first term, and that's the second term, and I'm numbering the term numbers up here, each number is multiplied by 1/2. You might remember this from our radioactive decay problem, where we start with a certain number here and multiply each succeeding number by 1/2. So the first number is multiplied by 1, and then multiplying and so on. So each term, so it turns out that this one is S of n is equal to 1/2 to the n power. Although, actually, to make it simpler, we're going to start with 1/2. Make that the first term. So 1/2 to the first power, 1/2 to the second power, 1/2 to the third power, 1/2 to the fourth power, and so on. Okay? So if I'm giving you a formula here, you can generate the value, generate the term, generate the formula, and it's not too bad if they're not too complicated. So let's try this one. How about guess this formula here? Okay? And then guess this formula here. Okay? So guess those. Okay, well this formula here, hopefully you can see if we're starting with the first, if that's the first number, the second number, the third number, the fourth number, the fifth number, can you see the pattern is that we're squaring them? So this is going to be S of n would be n squared. And this one here, can you see if this is the first term and that's the second term and this is the third term and that's the fourth term, can you see here that in each case we're cubing the numbers? So S of n would be n cubed. Now with these guess the formula problems, they require a little bit of deduction and a little bit of guessing and checking to see how they might work. Okay. Now, all right. So I'm going to stop this. Video right now. We've got one more on what are called recursive definitions, and that will be the next one. All right. Bye.